Hello everyone, in this video we're going to go over the solutions for the worksheet in week 4. So first we have a linearization to approximate the value of cosine of 3. As always, when we're trying to do an approximation, then we need to figure out what the function is. So in this case, clearly the function is cosine of x, and then we want to approximate by a point that is probably close. So a point that is close to 3 will be pi, which is 3.14. So we're going to use pi to approximate cosine of 3. So if we take as x equals pi as a point, notice that then the next what we have to do is to actually find out what cosine of pi is going to be, which is -1. And then if this is f, we're going to take the derivative f prime of x, which will be minus sine of x, and f prime of pi is going to be then 0. And so according to the linearization in x is going to be approximately, or f on 3 is going to be approximately the linearization on 3. But let me first go and describe what L of x is. L of x is going to be f of pi plus f prime of pi x minus pi. Okay? And so to approximate f of 3, then we have this first value of f of pi, which is -1, plus, and then we'll have that f prime of pi will be 0. And so we'll have that 0 multiplied by x minus pi is that. So we're going to have that f of 3 approximate to -1 as well, which is kind of makes sense since it is very close to pi. So this is an approximation that is valid for cosine of 3. Okay. Now for exercise number 2, we want to find the absolute minimum and the absolute maximum of the function f of x, x squared minus a log of x on the interval 1 to 5. So remember that when we have a close interval, the way that we do this is that we first need to find the critical points. So f prime of x is going to be 2x minus a over x. And we need to find out where this function is going to be 0 or where this function is going to be not defined. So we organize this function a little bit better. This is 2x squared minus 8 over x, or I can factor this 2. And this is x squared minus 4 over x. So f prime of x equals 0 implies that the top is equal 0. So x squared minus 4 is equal 0. And that's going to be x minus 2, x plus 2 equals 0, which means that x equals 2 or x equals minus 2 are the possible solutions. Now f of prime of x equals do not exist is going to occur when x is equal 0. So these are my likely critical points: 2, -2, and 0. But now, if we pay attention, we are in the interval 1 to 5, so we're really not going to care about this one, and we're really not going to care about this one. So the only values that I should care are going to be 1, 2, and 5. Since those are the values, this is the critical point that is inside of this, and I'm actually taking also the edges. So if I do f of 1, plugging in the original function, this is going to be 1. If I plug f of 2, this is going to be 4 minus 8 log of 2. And if I do 5, then this is going to be 25 minus 8 log of 5. Then, of course, I need to find out who is the maximum and the minimum of these values. And then the minimum most likely is going to be one of these quantities. And here you probably want to use a calculator to find out this value, since there are very specific values. So let's find out first. 4 minus log of 2, or 8 log of 2, is going to be, this is going to be minus 1.5. And now 25 minus 8 times log of 5 is 12.12. So this is clearly the max, and this is clearly the min. Okay, maximum and minimum values. And this occurs at x equals 2, and this occurs at x equals 5. All right. So now exercise number 3 is a very complicated chain rule. It has a lot of different compositions inside. So the best way that you can approach this is first establish this as two functions composed. So you get y equals 3 to the g of x, right? And so if we do that, then this is just y prime is equals 3 to the g of x times g prime of x. But then who's g of x? Well, turns out that g of x is secant of x squared log base 2 of 3x. But then this is a composition too. This is like secant of f of x. Okay? And so if we find out what g prime is, then this is just secant of f of x, tangent of f of x, and because this is composed in f of x, then it's going to be f prime of x. So the derivative of secant is secant by tangent, and because we multiply by the inside function, then by f prime of x. So this ends up being 3 to the g of x, and then I'm going to be multiplying here by secant of f of x, tangent of f of x, and then f prime of x. But then, of course, now we need to find out who f prime of x is. And so we just got to recall that f of x here is x squared times log base 2 of 3x. This is a product rule. So f prime of x is going to be 2x log base 2 of 3x plus, and then x squared, and then the derivative of this log is also a chain rule, but the derivative of log of base b is 1 over ln of 2 times 1 over 3x, but by the chain rule this also produces a 3, so it's going to be this. So at the very end, f prime of x is just going to be 2x log base 2 of 3x plus, and then this x squared cancels with 1x, this 3 with this 3, and so this is just going to be x log of 2. Okay, so now at this point we can write a very long result. This is 3 to the secant square of log base 2 of 3x, and then times secant of x squared log base 2 of 3x by tangent x squared log base 2 of 3x times, and then f prime of x, which is 2x log base 2 of 3x plus x over log of 2. So very long derivative, very complicated in terms of chain rule. But if you just separate the chain rule one with the other, you're always going to be able to just do one chain rule at a time. Okay? Now, on the survey from last week, I noticed that a lot of you mentioned that you were concerned about implicit differentiation. But implicit differentiation is not really that bad. When you think about it, you're just doing normal differentiation with chain rule. But the only thing is that every time that you make a derivative with y, then you're going to multiply by y prime. So for example, here we want to find the y dx, which I'm going to write, by the way, as y prime because it's easy to write it that way, given this function. So we have the derivative of this is going to be 2x times y plus, and remember this is a product rule, x squared times 1, because the derivative of y is 1, but because I'm taking derivative with y, I'm going to multiply by y prime. Now with tangent, the derivative of tangent is secant squared. So secant squared of y squared times x, but this has a chain rule here, this y squared times x. So the chain rule of this is going to be 2y times y prime, the derivative of y squared, times x plus y squared times x. And then this is going to be equals to, and so we have secant of xy, which derivative is going to be secant of xy by tangent of xy. And then by the stuff inside, which is going to be a product rule between x and y. So it will be y plus x y prime. That will be the product rule of x times y. So this is a lot, and the next step that we gotta take is that we actually want to separate things that are with y prime on one side and things that are without y prime on the other side. So let me put everything without y prime from this side. So 2xy, and now this secant square with this y square x, so plus y square x secant square of y square x, and then minus y secant of xy tangent of xy. Notice that I'm getting this piece with this. And now that's the part without y prime. Now let's put on the other side whatever has y prime. So y prime factor of, then we have here x squared. And then from here, notice that we have this 2yx secant square of y square x. That's just from this piece. So now I completed this one, I completed this one, and I'm only left with this piece, which is going to be minus x secant of xy tangent of xy. And so after this very convoluted step, then I finally find out what y prime is, which is the ratio between these two things. I'm going to be calling this a, so I don't have to rewrite it again. And I'm going to be calling this factor b. So y will be a over b. Okay. And that's it. So at the end of the day, a lot of the things is make sure that every time that you're taking the derivative of y, you multiply by y prime or by the y dx, depending on whatever you want to do. Okay, now for exercise 5, this is a very similar situation to what we had before. We're finding the maximum and the minimum in an interval for a given function. So first, let's find out what the derivative is. So f prime of x is minus 2, and then this is going to be minus x, and then this is going to be x squared. So this is a polynomial of degree 2. I can reorder this as x squared minus x minus 2. So I can probably factor this as something that multiplies gives me minus 2. But the sum gives me 1, so x minus 2, x plus 1. And so this will be f prime. Notice that f prime of x equals 0 implies that x is equals 2, or x is equals -1. Okay. Notice that in this interval -3/2 to 3/2, this is actually in there. This one is there, but this one is not. Since 2 will be 4/2, and we're only getting up to 3/2. Now, but this means that to find the maximums, we need to find the values for f of -3/2. We need to find also what f of -1 is, and we need to find what f of 3/2 is. Those are the three values that I need to find out. Of course, I can do this with the calculator, but probably my best bet is doing something in Decimus to find out more easily. In your test, you're likely not going to have to do this by hand or not with such a complicated numbers. So don't worry too much about it. But let me see what values I'm supposed to get. Okay, so I have -2x minus x squared over 2 plus x 3/3. And now I'm going to do f of -3 divided by 2. I'm going to do f of -1. And I'm going to do f of 3/2. So here you can see clearly who's the maximum. So this is 1.16, and this is clearly going to be the maximum. The minimum though is going to be on 3/2 because it's a -3, and this is a 0.75. So this is the min. Okay. And so this is what happens when we have this, again, closed interval. This is the way that we classify the maximum and the minimum. We find out who's the maximum value, who's the minimum value from either the critical points that we have inside of the interval or the extremes of the interval. Now for exercise 6, we continue doing linear approximation. We're going to have to approximate a 10th root of 1.03. So clearly the function that we're trying to use is 10th root of x, or if it's easier to manage, x to the 110. Because we're going for 1.03, then the most closer point that we can use to approximate is 1. So if we do f of 1, then that's going to be just 1, which is 1 to the 1/10, which is 1. Now the derivative f prime of 10, f prime of x will be 1/10 x to the 1/10 minus 1. And if we simplify this, this will be 1/10 x power to the -9/10. And then again, because we're approximating in 1, f prime of 1 is just going to be simply 1/10. Since any power of 1 is just 1. Now the linear approximation function is going to be f of 1 plus f prime of 1 x minus 1. That will be the linear approximation. And this means that this is 1 plus 1/10 x minus 1. And so now if we want to approximate the 10th root of 1.03, this is going to be 1 plus 1/10, 1.03 minus 1. And so this will be 1 plus 1/10, and this is like a 0.03. And so whatever this result is going to end up being, this is like 10.03 0.03 over 10. Since 1 can be seen as 10 over 10, and then it will be 10 plus 0.03, so it will be this number. Now, exercise 7 is a similar thing, but we want to find the equation of the tangent line to the function root to the 10 at the point corresponding in x equals 1. So pretty much is exactly the same linearization that we just did in here. So it is the 1 plus 1 over 10 x minus 1. So there are really two questions that they go with the same type of things. Now for question 8, we have a right singular cylinder is expanding so that the volume is increasing by 8 cubic meters per minute. And we have that given that the radius is increasing at a rate of 1 meter per minute. We want to know at what rate the height is increasing when the height is 3 meters and the radius is 2 meters. So first and everything, we need to kind of get a picture of what we want. And so we have here the radius, we have here the height, right? And so this is the right circle and cylinder. We have that the volume of this is pi r square times h. And of course, the rate of change of the volume is something that we have. The VDT is going to be 8 cubic meters. And we know that this is the rate of change of the volume because it's 8 cubic meters. And so that's a measure of volume. Now, we want to know, and we also have, given the rate of change is 1 meter per minute. And this is meter cube by minutes, and this is meter by min. Okay. So we want to know what is the rate of change of the height. Okay. And so one of the things is that notice that we're considering that this function is all in terms of time. So r square is really r square of t, and h is also a function of t. So if we calculate the v dt, notice that this, by the derivative of this function, this is going to be 2 pi rt. And if we're doing here, there's a product ruling here. So we're doing the derivative of the radius. So we got to multiply by the rdt. And because it's a product rule, then we multiply by h without doing anything. And then plus pi r square, since we're not taking derivative there, times h. But the derivative of h is going to be 1 times the h dt. Notice that we're doing some implicit differentiation there. Okay? We remember that h depends on t. So in reality, this is just essentially 2 pi r by dr dt plus, h, I forgot the h. 2 pi r dr dt h plus pi r square dh dt. Notice that we have some of that information. We have the r dt and it's 1, right? So what we're gonna get is going to be dv dt is 1 already because I have that information that dv dt, is 8. So dv dt is equals 8. And we want to know what is happening when dr dt is 1, but we have that h is equals 3 and r is equals 2. So we're going to replace r, and r is 2. dr dt is 1, and h is 3. So we're now replacing values, all the values that we have. Then pi r squared, so 4 pi. And then we don't know what the h dt is. This is the only one that we don't know. So now we have h, 8 is equals, and this is 2 by 2 is 4, by 3 is 12. So we have 12 pi. And here we have 4 pi dh dt. So of course I can put everything to the other side, and this is 8 minus 12 pi divided by 4 pi, and this is going to be dh dt. And notice, because this is in terms of length, this unit, whatever this is going to be in terms of meters per minute. All right, for exercise number 9, we have that we want to find the c that satisfies the conclusion for the mean value theorem for the function f of x, x squared on the interval 1 to 2. So first, we gotta review what are the conditions of the mean value theorem. So first, we check that f is obviously continuous on the interval 1 to 2. And f is also differentiable in the 1 to 2 interval. No issues with that. So I'm going to be able to have now the f of 2 minus f of 1 over 2 minus 1 is going to be equals to certain value f prime of c. Now we calculate what this is. Of course, f of 2 is going to be 4. F of 1 is going to be 1 over 2 minus 1. So this is like 3 over 1. And so this is 3. So this is essentially saying, hey, I have certain value where f prime of c is going to be equals to 3. Now, if we find out what f prime of x is, then that's 2x. So that means that f prime of c is essentially 2 times c. And if 2 times c is equals to 3, that means that c is equals 3 halves. And this is the c that satisfies the mean value theorem condition that we wanted to find. Now, for the last exercise, we want to use the method to sketch the graph that was given on the 4.5 section. So first, then we need to find out what are the critical points. So f prime of x is going to be 2x times x squared plus 4 minus x squared times 2x. That is the top over the bottom square. Now we can simplify this a little bit so we can manipulate this better. This is going to be 2x cubed plus 8x minus, and this is going to be 2x cubed over x squared plus 4 squared. Notice then at this point I can cancel the 2x cubes, and that's just going to produce 8x over x squared plus 4 squared. So there are two possibilities for critical points. Critical points are going to occur where f prime of x is equal 0. So that means the numerator is equal 0. That implies that ax is equal 0. That implies x is equal 0. And we also have f prime do not exist. And that will be where the denominator is 0. But x squared plus 4 is never 0. So the only critical point really is going to be, real critical point here at least, is going to be x equals 0. Now let's analyze what happens in the intervals. So according to the fact that we only have a critical points, then we can split the real line between the 0 and minus infinity and 0, infinity. Now we can test for certain points to look at the behavior f prime. So if this is f prime, notice that the denominator is always going to be positive. So the sign is just going to depend of the numerator. And so that means that over here is positive and over here is negative. With negative numbers, I get a negative. With positive numbers, I get a positive. Now that implies that f is decreasing in minus infinity 0 and is increasing on 0 infinity. So this is also telling me that this is a minimum. So x equals 0 is a minimum or local minimum. Okay? That information comes from here. That is for critical points. Now I want to have the same information but for concavity. So I'm going to need f2 prime. So f2 prime of x is going to be the derivative of this, which is 8 times x squared plus 4 x squared minus ax, and then the derivative of this, which is going to be 2x squared plus 4 times 2x. And of course, the bottom square. So x squared plus 4 to the 4th. Now let's simplify this a little bit more. So then f2 prime of x is going to become, and the best way to simplify this is breaking apart this binomial. So this is going to be x to the 4 plus 8x squared plus 16. And then this is being minus, and then I gotta multiply all this, and so this a by 2 16x cube, wait, by another 2, so it's 32, so it's 32 x to the 4th. X and x and x is x to the 4. And now for the last one, this is 16 by 2, 32, and 32 by 4. It's going to be 128. And then this is going to be x squared. And over x squared plus 4 to the 4. So now I get to simplify some of this. Notice that I have things that I can match up, at least in terms of x to the 4 and x squared. This is 8x to the 4 minus 32. This is going to be 26. Wait, 24. Minus 24 x to the 4th. And then we have 64 here, and this is 128. So this is going to be minus 64 x squared. And then we're going to have this plus 16. And then at this point, what we want to do is we want to be able to find out the zeros of this. Now, finding out the zeros of this particular function is going to be a little bit complicated. There are two strategies that you can use for doing that, and one of them is consider this like a quadratic function. So this will be like, consider this minus 24 u squared minus 64u plus 128 equals 0. And once that you find out what are the roots of this, then you remember that u is just going to be x squared, and then you find the roots by using the square root on both sides. Okay, but one way of also doing this would be graphically. So in this case, because it's not the exam or it's not something else, you can support yourself using something like your calculator, your Desmos calculator. And so let me just do that. So if we have, we want to find out about the zeros, we have this minus 24x to the 4 minus 64x squared plus 128. And we need to find out when this is going to be 0. If we check the graph of this, you notice that this is going to give you in this points. And this point is where it crosses here, minus 1.1655 and 1.155. So those are going to be essentially the critical points of this. So f2 prime of x equals 0 means that x is equals minus 1.155. And also x equals 1.55. Those will be the two possible values that we're going to get from finding the solutions. So now what's going to happen next is that we need to also do a sign chart. And we're doing a sign chart with minus 1.55, 1.55. And so this is going to help us see what is the concavity of f2 prime. So we're going to, in the sign of f2 prime and then the concavity of f. So first we're going to take a number. So for example, we do 0, which is going to be in the middle of this 2. Notice that this goes to 0, this goes to 0, and it's going to be 128 over something positive. The denominator is always positive, so we're going to be fine with that. And this is going to be positive. Now for the numerator, notice that whatever we plug is going to be positive, a positive number adding up in here. So regardless of what number we take, the behavior in the positive or negative after 1.55 is going to be the same. We can make that evident. Let me call this g of x here. And so now let me calculate g of 2. Notice that is minus 512. And notice that when I do g of minus 2, I'm probably going to get the same, minus 512. So indeed, this is going to be a negative and negative. And so in terms of concavity, means that this is concave down, this is changing to concave up, and this is changing to concave down. So now we know that this 0 is the local minimum. And so now we have enough information to kind of graph what this is. We know that f of 0 is going to be 0. And we can also find asymptotes in here. And you realize that when you take the limit when x goes to infinity of x squared over x squared plus 4, and notice that it can be plus or minus infinity. It doesn't matter, it's going to be the same. When I take the limit, this is going to you can do it by L'Hopital's rule or whatever you want. This is going to be essentially 1. Okay, because it's going to give me at some point 2 over 2, which is going to be 1. And so this means that the asymptote when we're going into the infinity is 1. So we have this situation where this is the axis, is crossing 0, and then before 1.55 and minus 1.55, the function is concave up. So you have this situation, and then you have this situation here. But then there's a change in concavity here, and it does something like this. And it flips, and it's never going to be more than 1. So something very flat like this. This is the graph of this function. And so if you want to verify that, we can actually use the Desmos as well. And so if we check this out, notice that x squared over x squared plus 4 is following the same shape that I just mentioned. We can superpose the top just to check that the changes in concavity occurs precisely on the point where the second derivative have their inflection point change. Okay. All right, so that's a big example on how to sketch graphs. And this is the end of the worksheet for this week.